class. Today will be a little bit different. We have two classes with same group, the same content. Today we have a special guest. As you guys know, this is my colleague, my friend Randall Beatty. He's gonna be presenting uh, a lot of good information about quantum computing and cryptography. That stuff that he is specializing in. I'm gonna let him introduce himself about what he does, the experience, what the content are. This is a 1 hour presentation, 45 minutes of presentation ish, and then we're gonna have some questions. So I do encourage you guys to make any questions, like raise your hands. I can ask, or you can ask directly. This is your opportunity to talk to someone with very experience in the field, very smart, and I'm grateful to be here, for him to be here. Randall, thank you very much to be here to our class at the Houston Christian University, and you're good to take it over. Let me maximize it here.
Sounds good. Can y'all see my screen okay?
I think so. It's not maximizing though. Let me see. It's not maximizing. That's all right. I think we can proceed. Thank you very much. I'm gonna close
Okay,
the camera here.
sounds good. Hello, everybody. As Otto mentioned, my name is Randall Beatty. I am the enterprise security architect here at Dell Technologies over public cloud security and data security. Data security is kind of a wide field. We cover a lot of different areas in that include database security, endpoint security, securing north of 300,000 endpoints. Dell's a very large company, and we have some very large data centers as well. We have cryptography, what we call data stewardship, which is things like DLP, data categorization, data labeling, those kind of works, as well as some associated capabilities like file integrity monitoring, database activity monitoring, things of that nature. Me personally, I'm a father of two. I have adult kids. I got my bachelor's degree from Angelo State University in 2007. After that, I became a software developer. I did software development for about a decade, working in everything from mainframe languages like COBOL, PL1, RIX, a lot of old DB2 stuff on mainframes, moving up through JEE, so Java Enterprise Edition, on some old monolithic web app stuff, all the way into reactive frameworks like APIs, reactive front ends, JavaScript driven front ends, single page apps, things like that. During that time, I got interested in cybersecurity after working on some cross-site scripting defects that I was able to find an infrastructure fix for, working on a claims infrastructure team at the time for an insurance company. That kind of lit my fire, and I started to go and get my master's degree again in computer science, but focusing in what they call computer and information security. I got that degree from UTSA. In 2017, which is when I entered an architecture role over what they called secrets management, which is an identity and access management field. I did that job for a couple years, moved over to Dell about 5 years ago as a senior manager over data security. I did that for about a year and a half, decided management wasn't really for me. So went back into architecture where I became the public cloud architect. Did pretty good at that for about 6 months time. At which time our data security architect left, and I got what I like to call congratulations, which is, hey, you've done a great job with the cloud security architecture stuff. So congratulations and condolences. You get to do somebody else's job as well. So now I do both of those roles. And that's where we are today. As Otto said, I have about 30, maybe 40 minutes of content here. If you have any questions during, feel free to ask. If you want to save them till after, that's fine as well. We can rip back through anything. I'm happy to answer questions at the end about anything. It doesn't even have to be about this presentation. If you just want to have a discussion, I'm totally open to that. The agenda for today, we're first going to cover what quantum computing is, what quantum computers are out there today, the threat posed by quantum computing, well, a threat posed by quantum computing. There's possibly more than one. I'm only really deep on one. what a cryptographically relevant quantum computer is, and when we can actually expect one, so when that threat becomes real. Some of the mitigation strategies that have been put in place for them and what we're trying to do, and then looking forward for where the industry is still headed. I think a lot of it will be pretty interesting. Unfortunately, some of them will be pretty boring as well. There's a lot of standards talk that we have to go through that's going on with this, a lot of NIST stuff. But the reality is that's the nature of the beast a lot of times. So let's just go ahead and get going right in. So what quantum computing is, right? So quantum computing leverages the principles of quantum physics, particularly superposition and entanglement, to perform calculations beyond the capabilities of traditional computers, potentially revolutionizing fields like medicine, AI, and cryptography. On the right there, we have a picture of one of the quantum computers they have today. So you see these things look very, very different than traditional quantum computers. They're still really not all that powerful. We'll get into that a little bit here in a bit. There's still a ton of work to be done in this space, and there's a lot of questions about what value they can actually bring. Things unique to quantum computers, got a few definitions here. Qubits. So unlike in a traditional computer where we have transistors, right? And a transistor is either going to be in a 0 or a 1. So it's binary, right? It's in either one of those states. A qubit can exist in both states simultaneously, or even anywhere between those states. There's an infinite number of positions between those spaces. So those can be any of those and even multiple of those at a time. So that's where you get superposition, right? It allows them to make multiple calculations at once. With a classical computer, you can have multiple threads going at a time, but each clock cycle is doing one instruction operation, maybe 7 or 32 or 64, depending on how many threads you have. But it's doing one of those per thread. This one can do multiple operations per qubit. And then entanglement, right? So 2 or more qubits can become linked, meaning their fates are intertwined, even if separated by distance. Measuring one entangled qubit instantly reveals information about the others. It gets pretty deep if you really want to dive into there, right? You're gonna have to get an education in quantum physics to really go and get real deep into what that all means and how that all works. But it's really interesting and could help us to solve a subset of what we call NP problems that are really interesting. So non-polynomial. I don't know how far y'all are along education. I should have probably got that information. But if you ever taken a computer architecture class or algorithms class, you learn about big O notations and polynomial time, non-polynomial time, NP complete, NP hard problem sets. They're really interesting problems that traditional computers really struggle with. Quantum computers will help us solve some of those problems. Some, not all, but some of those problems that we struggle with today. And also come up with new ways to solve problems we don't even know we have. So here's a little comparison, right? So we already covered qubits versus transistors. The power increases exponentially in proportion to the number of qubits, while power increases in a one-to-one relationship with the number of transistors. Quantum computers have a high error rates and need to be kept ultra cold. That's something that is a limitation today. We don't know that that'll always be a limitation, right? There's again, a lot of innovation going on in the field, a lot of work happening. So where classical computers have very low error rates and can operate at room temperature. Yes, we keep them cool because all those transistors create heat. But at the end of the day, they're still very, very warm, right? They're running usually sub 100 Celsius, 95 Celsius or whatever. These we're talking are trying to get as close to 0 Kelvin as possible to keep things from going crazy and erroring out and causing all kinds of problems. Error correction is still a very, very hard challenge with quantum computers today. Quantum computers are well suited for tasks like optimization problems, data analysis, and simulations, where most of the stuff we do with computers today are actually best done by our classical computers that we're all used to working with. So the threat posed by quantum computers, right? So quantum computers threaten the security of current widely adopted public key crypto systems. So when I say public key, that means PKI, public key infrastructures, primarily asymmetric encryption, right? So you have a private key and a public key. The private key stays private to the owner of that key to encrypt his data. He can share the public key out there to anybody that needs the public key. They can decrypt the data. Only people with that public key can then read that data, and they can also validate, they can, repudiate that data is only from that sender. And then vice versa works as well. Everybody with the public key can encrypt any data, and the only person that would then be able to read it is whoever has that private key. So this is done heavily today with certificates. So TLS, how we communicate on the internet securely. The primary two that we use are ECDSA and RSA. So EC is the elliptical curve algorithms that we use, and then EC stands for elliptical curve digital signing algorithm, right? And then there's RSA, which is probably the one that you're used to seeing a lot more of. ECDSA is a good bit faster. It's still up and coming, but quantum is really going to get in the way of that. And then key establishments using the Diffie-Hellman algorithm as well, and RSA can use that too. Quantum computers have changed what we believed about the hardness of mathematical problems that underpin cryptography. So really the big problem that underpins PKI is what they call prime factorization. So it's finding the factor that is of extremely large prime numbers. It's a very, very, very hard problem for a traditional computer to do. And, brute forcing existing RSA 2048, right? I think the last estimate that I saw would take every computer in the world joining all of their forces together about 400 years to crack, which makes it essentially uncrackable, right? Because that data would probably not be very useful in 400 years, considering everybody's dead. However, using Shor's algorithm, which is an algorithm we'll cover here in a bit in depth, makes this problem quite easy. It puts it all the way down into what they call polynomial time, which is, it could break this in hours. A single quantum computer can, once we get to that quantum relevancy. Quantum computing also impacts the security strength of symmetric key-based algorithms. So this is usually what you use for data at rest, right? Just regular old everyday algorithms that you would have to worry about here. AES being the primary one that you're probably used to seeing. So Grover's algorithm provides speed up to break these things, but the fix to that, right, is just to increase the key size. And then we're really kicking that can down the road to have the same problem where it's just too hard to do it. Eventually, right, you're going to have to continue making those bigger and bigger. It might make sense to come up with better algorithms there. However, the focus today is on PKI and ensuring that problem can be fixed. Simply said, without quantum resistant encryption, everything that has been transmitted or ever will be transmitted over a network will be vulnerable to eavesdropping and public disclosure. So areas of high risk. Right? So we have three primary areas here: forged signatures, being able to impersonate identities online, digital identities, be it for your bank, be it for anything, right? All that stuff is encrypted today, and if they can decrypt that, they can then replicate that super easily and forge those signatures. What they call man-in-the-middle attacks. Again, I don't know if y'all have talked about a lot of this stuff yet. What a man-in-the-middle is, you talking to your bank. TLS gives you usually a guarantee that you have end-to-end encryption here. So anything that you're seeing on your end was decrypted on your laptop within your browser, and anything that's seeing on the bank end was decrypted on their servers. Anything that's going across that wire is fully encrypted. So imagine now if there's someone in the middle intercepting this, decrypting everything and looking at what you're doing. You're trying to, make a deposit from one account to another. They modify that in the middle, move that money, redirect it as a man in the middle. And then a big one, and probably one of the biggest threats to it right now, is what we're calling harvest now, decrypt later. So think of things that you need to keep the data around for a long time. Let's say the data needs to stay around for 20 years for whatever reason. They can be capturing this data, moving over the web. They can be collecting it from data breaches, doing anything that's encrypted. They can't access. They can't do anything with it. But they're already, just storing this data up, waiting until they can. Then they'll crack it later and see if there's anything of value into their in that data at that time. So quantum processors today. So funny thing about this slide, I built this one yesterday. I was looking at the dates of these announcements, and pretty much all of these announcements have come out in just the last 5 months. I think Novera dropped in November. Majorna was last month. Willow was in December. and then Condor was just in January as well. So these are quantum computers that are available today, right? Novera from, I can't remember the company's name. Anyways, they have a ready to ship 9-qubit computer today that's ready to execute and run within your environment if you have the electrical resources in this space to set it up and run it, and you can actually use it to solve a problem. Most people really can't today, so it has very low sales, right? This is a very up and coming area, so if you're choosing to invest here, be very careful. Then Google just announced Willow, their state-of-the-art quantum chip. You can see the size of the chip there. And I think it has 100 qubits on it. Still has a very, very high error rate. So it is not cryptographically relevant, but it is out there and able to be run with in a more traditional package. Microsoft's chip is a new type of qubit that they're working with. They are saying that the way that they built the chip can scale up to 1 million qubits, which is where we start to get to cryptographically relevant range. But that chip you see there only has 8 qubits on it. And then IBM broke the 1,000 qubit barrier first with their Condor supercomputer. Now theirs still has some high error rates. The challenge that they're having is keeping it cold enough all the time, and also that it's only competing with a quantum computer half its size called Osprey. But they also believe that this new design that they used for Condor will allow them to scale up larger, where Osprey, right, was not going to be a scalable design. So that's just the state today, where we're at, where they're trying to get to. Well, I wouldn't say they're trying to get to cryptographically relevant. That's where it's going to go naturally. So a definition of a cryptographically relevant quantum computer, all this stolen from Wikipedia. I know it's not a legitimate source for a lot of the work you do, but it is for me. So we're going to use it here. A cryptographically relevant quantum computer is a quantum computing system powerful enough to break modern cryptographic algorithms and secure digital communications. So in practical terms, it is a large-scale, fault-tolerant quantum computer capable of running quantum algorithms like Shor's algorithm that we covered earlier to crack the cryptographic schemes that underlie today's security. So CRQCs will be able to run 2 algorithms that impact cryptography. We talked about them both earlier, Shor's algorithm and Grover's algorithm. So Shor's algorithm breaks PKI, namely RSA, Diffie-Hellman, elliptical curve, Diffie-Hellman, and ECDSA, which again underpin the internet in the way that it works today. So Shor's and Grover's algorithm, right, is more applicable to symmetric encryption. From there, there's a couple of explanations there. If you really want to go super deep into these things, feel free to go look up their Wikipedia pages, some of the explanations of how they work, or go even deeper and go look at the white papers that are linked there and read up some of those. It gets very, very heavy into math very quickly. Again, algorithms was a tough course for me. I didn't think I did well in it, but I passed and I'm here today. So good luck when you get there. Cryptographically relevant quantum computers. So this is a 2022 opinion-based estimates of the cumulative probability of a digital quantum computer able to break RSA 2048 in 24 hours as a function of time frame when it will be there, right? And so this is just predictions, right? So the circles are the optimistic times that we'll get there, and square being more pessimistic. And these are percentages of chance, right, in between those. Generally, the industry's leaning that it could be up to 25 years. The challenge is that we don't want people kicking the can down the road, waiting 20 years to fix the problem whenever that actually just pops up all of a sudden. Chances are during this timeline, there's going to be a couple of big innovations that'll really speed this up, that it won't be quite linear like it looks like here. It'll be more exponential when that comes along. And that leads into a fun discussion about Moore's law. Again, I don't know if that's something you discussed yet, but Moore's law is the observation that the number of transistors and ICs, so traditional computers, doubles about every 2 years. Moore's law is an observation and projection of a historical trend. The challenge here is that we do not know enough about quantum computing today to say that Moore's law is going to apply. If it did, we could come up with very accurate predictions, but we just don't know. So we will probably be able to measure that in another 10 years. That could be too late. 10 years, I say we have an up to 27% chance of having a cryptographically relevant quantum computer. This graphic here is just showing traditional computers and the growth at which the transistors went. And you can see that it is a logarithmic scale here, showing that this pretty much 2x growth as we went along from this 1970s to now. I know y'all might have a small picture there. So mitigation strategies. So a lot of these slides were taken from a NIST presentation that was given at the PKI Consortium just a couple months back at the University of Texas in Austin. I was there representing Dell. Really interesting stuff. A lot of the people working on the front lines of this. Still a whole lot of churn about what to do, where to go, and things that need to happen, right? So this is kind of the timeline of the NIST PQC standards. So 2010 to 2015, they built the project team and had the first PQC conference. At 2016, they determined criteria and requirements and had their first call for proposals. In 2017, they received 82 submissions. 69 of them became first-round candidates. In 2018, they had the first NIST PQC standardization conference. The next year, they announced 26 second-round candidates. They released a paper 8240 to start reading up on some of those, right? And then held the second NIST PQC standards conference. In 2020, they announced the 7 finalists and the 8 alternates as they continued working through these things. And then in 2021, they hold the third NIST PQC standardization conference. In 22, announced initial selections for the standardization and then the 4th round candidates. And then in 2023, they released the draft and the final call. And as of August of last year, so this is how hot off the presses this is, right? They actually released the final standard here. So now we have 3 standard algorithms available to us that are published in FIPS 203, FIPS 204, and FIPS 205. So there is a module lattice-based key encapsulation mechanism based on Crystal's Kyber. They have another one based on Crystal's dilithium, which will turn into MLDSA, as well as some based on what they call Sphinx. Finally, there's one that's under development to be released very soon called Falcon. We'll see how that one comes along. They're saying early this year that one should be standardized as well, which would be great to see because there's some real challenges with some of the algorithms that are already developed today. And we'll talk about some of those now. So the first one and the second line here, these are classical PKI algorithms, right? So we have RSA 3072 key size, and then we have ECDSA 256-bit key size. So now you can see that the amount of bytes that the public and private key sizes themselves are, and then even more so the signatures, which are usually what you're transmitting over the wire, right? You can see how much larger the signatures get when you move in to the different post-quantum algorithms. And we'll talk about why that's going to be a problem, right? So these are the things that they're looking at replacing and what PQC categories are going to go in. Kind of ignore that for now. What's really important, right, is this scale up on the key size, right? Here we're looking at almost tenfold, over tenfold key size. Here's a tenfold signature size. Why is that a problem, right? So today, the way the internet works, right, whenever you go and link up to a website, you go through the TLS handshake. You tell the server hello, it tells you hello back. Then you send so the SYNAC synchronization happens there. Then you send out your key shares to establish your communication protocol. Then you share certificates. Then you're done. You have a connected session. That's TLS 1.2. This one here is the TLS 1.3 handshake, which puts that down one negotiation level, which is nice, but most things are not using TLS 1.3 yet. It is the latest standard. It will support PQ certificates whenever those become available. The challenge that we have today, right, is our current our current translation of, or our current sharing of certificate protocols, right, takes about 1,248 bytes. In the future, we're looking at over 14,000 bytes, right? So this is a 14-fold. Now, yes, you're talking 14K down from 1K, right? It seems like a very small problem, right? Like you're not going to run into a huge issue with that. And generally, if you were connecting to one single website, you wouldn't have that problem. Unfortunately, for some, the way the internet works today, whenever I connect to like CNN.com, on the back end, there's 30 other web connections happening there, right? There's tracking cookies, there's advertisement sessions, there's JavaScript being pulled from remote places, there's CDN servers to go and get content, right? That's the part that we're going to run into a problem, because not only is this done on the website that you're hitting, the website or in your browser is calling out to tens, 20, 30, even 100 other sites at times, and pretty much using the algorithms as they are today, the signature sizes as they are today, quite simply, it's not going to work with the way the internet is designed today. So there's still a huge problem to solve in this space here. So transitioning to PQC standards. So NIST has released IR 8547. They are releasing that now. So the comment period ended January 10th of this year. The public draft is on November 12th. So it identifies quantum vulnerable standards, talks about how we're going to work with these quantum vulnerable standards and what we need to do going forward, and proposes some timelines going forward for quantum vulnerable algorithms. So 112-bit security strength will be deprecated after 2030, disallowed after 2035. 128-bit and higher security strength will be disallowed after 2035, which is coming very, very soon, right? 2030 is in just 5 years. When we still don't have algorithms today that can even work with the traditional internet. So you're starting to see that time crunch that we're in, right? NIST approved symmetric primitives providing at least 128 bits of classical security continue to be approved. So that's the symmetric AES stuff that we use today, usually for data at rest. So that's one government agency. There's also another government agency called CNSA that has their own timeline, and everybody was pushing for CNSA to extend their timeline because everybody that works with the government will have to apply to CNSA 2.0 will be applied to them. NIST is kind of the standard setting for the industry, while CNSA is, hey, if you're a government contractor and want to work with the government, you have to follow these timelines, right? So by 2030, you have to have software firmware signing, right? It is the default and preferred thing to have. They're releasing things that we've seen today that says to continue to do business going forward, we have to have the system signed with PQ algorithms no later than 2030. Web browsers, servers, and cloud services, right, by 2033. Traditional networking equipment by 2030 as well. Operating systems, niche equipment, custom application and legacy equipment, all by 2033. What's funny here is the industry was pressuring them that 2030 and 2035 was too soon, and we're going to have problems meeting those timelines. And they came back with an update where they shaved even 2 more years off of it. So that's kind of reminds me of dealing with children in that, oh, you think your 2 week is bad, you get a 4 weeks now, just the opposite. So now they're making it even harder, tightening those timelines even further. There is a huge amount of companies working on this together. So the NIST runs the NCCOE, the National Cybersecurity Center of Excellence. These are all partners within the NCCOE. You'll see the company I work for, Dell Technologies, is on there, as well as a lot of different cryptography companies, cert management companies, ISPs, right? There's a whole lot of who's here. It's very important that we get this problem solved sooner than later, and that we keep working towards resolution to get there. Looking forward, so a lot of work still remains, right? How is this going to work in operations? How are we going to modernize our infrastructures to be able to use all of these new signature types, right? There's still systems out there that have to run TLS 1.0 which has multiple known vulnerabilities in it, but has to be done just because they're so old, right? Think about our little mobile devices like these. This phone has a trusted computing module in it that has specific, what they call ASICs, specific transistors and processors in there that are built to hold a specific number of digital signatures and keys and things of that nature. That means that this phone will not be able to even be upgraded to PQ standards when that comes. Embedded devices that are out there today, we're looking at 90%, 95% of those not being able to support quantum algorithms. So there's huge change to be done there as well. PQC adoption in software and systems, talked about there, hardware acceleration support. So there's really two types of HSM vendors out there, right? I've worked with many of them over the years. HSMs are hardware security modules. They're places where we can get guaranteed strong entropy to get guaranteed strong keys, and it protects your keys in a untamperable piece of hardware. You can make them non-exportable. There's a few other things you can do. They're pretty interesting little devices if you want to go poke around. If you really want to play with one, you can actually get a USB-based HSM from Fido, who does the little hardware security keys. I think they're about $600 or $700. They're not cheap. But if you ever wanted to play with one, that's probably the cheapest way you're going to be able to do that. That said, the legacy providers out there still don't have support, much less hardware acceleration, because everybody's kind of waiting to see what gets standardized. It's really expensive to design and stamp and print hardware. So those companies are waiting to do that, because if they start doing that now and we change in a year to a different algorithm that gets accepted, and that's the one that finally gets adopted to TLS 1.3. Now nobody's really going to use those older algorithms, and they spend all that time tooling up and designing that hardware that doesn't get used. There's a couple vendors out there that are using FPGA arrays, so that's a functional programmable gate array. So really, it's programmable hardware. They're pretty neat. There's a nice emulator system out there called Mister that runs on one. The challenges are, right, that they're not really going to have acceleration. They'll have support, but they're going to be slower than ASICs that are custom built for these things. So that's holding some implementations back. Implementation in cryptographic libraries, right? Don't roll your own crypto. Use libraries that are out there that are part of the industry. The reason that those libraries are out there, and there's a handful of them that are trusted that everybody uses, is because they were written by very, very smart people, and they have known strong algorithms used in them, known methods for implementing those algorithms and using those algorithms. So those low-level libraries still need to get upgraded to support these different PQ algorithms as they come along, and then all the software that's built on top of those will need to get upgraded, right? Not to mention the hardware that those run on need to get upgraded. So there's just a huge amount of impact and work still to do. Protocols and application standards. I can lean back on TLS 1.2, which is what's used widely across the internet today. It will not be upgraded to PQ. TLS 1.3 is what everyone's going to have to use, which is not a simple in-place upgrade. Keys are larger, certificates are larger. A lot of server systems, things like API gateways that run for API-driven communications, can't handle the larger keys and the larger signatures, right? These things are already running at like 80% utilization, and going up to TLS 1.3 just topples them over. And finally, the algorithm standards, right? There's still a lot of those being developed, which we're going to jump into next, I believe. Yes. So there's still some more standards being looked at. Again, they're trying to solve the key size, signature size, signing time problem. So they're going to continue looking at some more. So the first three, right, those were finalized on August 13th. Those are the ones we already talked about. Falcon, FNDSA, is active and under development. And the NIST is making fourth round KIM selections in 2024. That did not happen. It's still going on. So they have classic McEllisey, Bike, and HQC. Psych was already disqualified, found to have some core vulnerabilities, and it wasn't going to work. So NIST has called for additional signatures in 2022 to evaluate general purpose signatures based on diversified math problems. 14 algorithms were selected for a second round and are continuing forward. So here's a list of those different ones. don't grill me on this low level cryptography stuff. I am not a cryptographer. I'm glad that we have very, very, very smart people working on this stuff. So these are some more of the problems that are actively being investigated to find other ways to solve this same problem. So these are continuously being worked on. We'll see where they go going forward. And I think that's about all I have. Oh, no, one more. Okay, so recommendations in FIPS 140 testing. So FIPS is important because it's a type of certification that the different HSM companies, software vendors, and people like us that build stuff for the U.S. government have to have and use in order for them to consume it, right? It's a strict definition of what type of functions and capabilities it has, what it can't have, things like easy key export, key replication, right, or a specific number of vulnerabilities, things of that nature. So NIST is actively working on special publications to provide recommendations for usage of PQC standards and applications. So they have special publication 800-227 coming out, recommendations for key encapsulation mechanisms to use KIM in key establishment protocols. So that's to replace Diffie-Hellman. They have guidance for the transition in the past and will provide PQC transition guidance going forward. NIST is already transitioning to new PQC algorithms for FIPS 140-3 validations. Most stuff out there today is only 140-2. 140-3 is the new FIPS standard that everyone's getting measured against. I think there's only been a couple of things that have been certified with that. And that certification process does take up to a year to get done. So even when these companies finally do build that hardware, which they haven't built yet, they then get in line for another evaluation that's going to take a full year to do to see if they can actually be FIPS certified. And that's it. That's where I finish my presentation here. Hopefully you learned a little bit. Hopefully I didn't lose too many of you and you're not all sleeping. I know it's a lot, kind of drinking from the fire hose, but it's an interesting state of the world, interesting state of a problem. There is still a ton of work to be done. There's still a lot we don't know, and still a lot of challenges to overcome. So we'll see how this goes.
All right, Randall, thank you very much. It's a very good presentation. I do have a question. Let me start. From the predictions of the use of the quantum computing to break and impact the cryptography standards, what is your personal takes on that? Do you think it's going to evolve faster than predicted? Do you think we're going to have AI impacting negatively or positively in it? What are your personal takes on it?
I wouldn't call myself a Luddite quite yet, but I think that both AI and quantum truly revolutionizing things are going to be a little further out than many think. Quantum, I think we're in that 15+ year range. I would not be confident that something's going to come quicker than 15 years. I don't know if you saw Jensen Huang on stage the other day, but he more or less came out and poo-pooed quantum in general, saying that it's not something you need to worry about, that everyone needs to be paid attention to AI. I think that's more of a stock market manipulation and sales strategy. But that's me. People talking about how AI is going to lose everyone's job this year and going to be taking over all of that stuff. I don't believe it's quite there yet either. I've had extensive experience with a lot of the different AI tools out there. And they are wrong a lot. They still have a lot of challenges. They have a lot of benefits. They can do a lot of neat things. I am more of the position that we still have what they call AI winter ahead of us, right? ChatGPT 4.0 is the one that ChatGPT came out, changed everything. I was like, oh my God, look at this, right? And that's kind of what kicked off this new AI discussion. There was a ChatGPT 1. There was a ChatGPT 2. No one really heard anything about it. It finally got good enough to where people are hearing things, right? So this work's been going on for years, for decades behind the scenes. Finally, something got important. I see what they call an AI winter, where we're kind of at peak interest, peak hype. We're going to come back down a little bit. We're going to find some new applications for it. It's going to find some interesting things. There's going to be some other exciting things happen. I put that more on the 4 to 5 year range, where AI is really going to have something come out. And we may possibly see that first AGI. So
great. Okay. Any question from the class? Yes. So you can come close here because the microphone is closed here.
So you mentioned that like whenever
Can,
using
can you hear it well?
I can hear him
Randall?
all right. Let him go and see what we
whenever
get
you're
through.
using like consumer electronics, right? You said how like currently they don't have it. So whenever they do implement it, do you think we'll see more of like wasted like devices, like consumer devices just thrown away because moving to like quantum computing? Or would it be more like new companies coming up and then, oh, here we have quantum computing? Because I remember AI Pin whenever they were starting up and they had like they were making their product just based around AI Pin or the AI, but then that didn't go well. Would we see more companies like that, or would we see more companies implementing like quantum computing, like you said?
You'll see both. I think you'll see some early companies coming in, doing some heavy duty innovation, creating new products, creating innovative solutions to problems that existing products have. A lot of times what you see with those small niche companies though is they get bought up by the big players, so they can buy their IP and implement that internally. I also guarantee you all of these consumer electronics embedded devices are working on these exact same problems today, right? All the way down to smart TVs, right? They have certificate management built in because they communicate over the internet, right? They're going to solve this in time. I'm confident that the industry is going to be able to solve this problem. We're working on it as hard as we can now. I am not confident that it's going to be by 2030 and 2033. I am confident that it'll be solved in time. But to answer your question specifically, I think we'll see a little bit of both. I don't expect that we will see some huge new consumer electronic that's gonna solve this thing or be really neat or some niche product. In the industry, we've seen some neat products, right? There are some PQ native HSM guys that have come out that have full algorithmic support for all of the post quantum algorithms that we have today. Where we have the old school players that have been around for years and years. Not to call out anybody specifically, but Taliesin and Cypher, right? That do not support these things yet, right? And we're already at this stage, and they still don't even have that support ready, right? What we'll probably see with those companies of that size, right, is that they'll let these smaller companies develop that over time, and eventually acquire those companies to just pull in those products and then push those forward.
All right, thank you. Any other questions? Come here.
Do you think that any
Come here. Say hello to him.
Well, do you think any spontaneous developments with either quantum computing or artificial intelligence could perhaps move up both timelines if they impact each other?
Absolutely. That's a really good question. Spontaneous developments in quantum are super hard, right? Because the amount of science that it takes to do these things, the amount of electricity that it takes to run these computers, the amount of technology it takes to keep things, that cold, it's very, very slow. Could somebody possibly innovate some small new thing that drastically increases that? Absolutely. In fact, that's what I expect to happen in AI. You know how I talk about how there's going to be another nuclear winter or AI winter, where things kind of slow down and lull. What I think we'll see come out of that is the same thing we saw come out of GPT as it advanced, right? That it was very, 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 very slow, and then boom, here's this huge impactful technology. I expect the next one that we see coming out of that will be what they call AGI, an artificial general intelligence, which is where the true world-ending AI threats, which I don't think it'll be anything like that. But that's where that actually comes, right? Where there's some true paradigm shifts in the entire thing. Then is it possible that AGI could solve some of the quantum problems, quantum design things, help us design some of those? Possibly so. Is it possible that quantum computers can help with AI algorithms? Absolutely, right? Because they'll be able to think and solve multiple problems simultaneously. AI algorithms today, while deterministic, are running on traditional computers, right, and take quite a lot of power, as we see from the different GPUs that are getting developed, the different solutions, the different AI computers, the servers that the company is selling today, right? That takes a huge amount of power to run that stuff. I'm confident that there will be some quantum algorithms that will be applied to AI that will solve portions of the AI problems that we have today with performance.
All right. Okay, come here. Let's say hello to him.
Hello. When talking about like the industry standard, is this focused mostly on the US industry or is this more international? And how do you think international cooperation between different groups will focus more so on improving quantum?
So good question. So NIST is the National Institute of Standards and Technology. What they released does apply to US companies. That said, NCCOE here, right? Thales Trusted Cyber Technologies is a Israeli company. This is a US standard of that, right? These countries that's here, PQ Shield is from Germany, right? So this is a multinational company COE here that's pushing on these things. Will there be international standards? Absolutely. The way international standards work today is you actually have NIST, you have other country-based standards organizations all working together to publish things like ISO 27001 and ISO 27002. I know Otto's familiar with those. You will get familiar with those, right? There are international agencies. Whenever I was at the PKI consortium, for example, there were 23 countries in attendance, and there was only 200 something people there, right? So that shows you this is a global size problem that is being worked simultaneously across the world. As far as quantum developments in the computers themselves, again, yeah, I mean, there's multiple countries working on those that have the resources, right? China has had some good developments. They've also had a couple of debunked white papers where they announced things that were untrue. Germany has some really good research going on. There's a company in Switzerland that has some really good stuff happening. There's a couple companies in the US that are working on this heavily. So yes, we will see international standards. A lot of those standards that come out will line up with US and other governmental standards agencies.
All right, so I think we have time for one more question. Any other questions? Don't be shy. All right. I think that's it. Randall, I would like to, on behalf of the class, thank you for your time to spend time and talk about that hot topic nowadays. It's hard to see someone with your knowledge presenting to the students. I really like to thank you for that. Appreciate your time, and thank you again.
Yeah, thanks for having me. I hope everybody enjoyed it. If you come up with any questions later, feed them to Otto. He can feed them to me. I'll be glad to answer them ad hoc. So
appreciate it. Thank you very much.
goodbye.